Okay. So here is the event. It's just the subset of sample space that includes all the even outcomes. Um, so hopefully that's what you got. Um, and that's how the event's defined. Then you can imagine that the odd event now, if this gave you any difficulty, then you can probably imagine that the odd event is going to be defined as this. And there's the event here of E less than 4. Now, so, and then here's a question for you. So if you want to write this down, that the outcome is less than 4, you could write that down. Then the question is a question about the term mutually exclusive. Is the even event and the event of the number being less than 4 mutually exclusive? So why don't you take a moment and see if you can answer that question, and I'll wait a little bit, and if you can um, figure it out, or if you're present, raise your Zoom hand. Okay, so here is the event of the outcome is less than 4. You've got 1 through 3. So the question, are these two events mutually exclusive, is asking, as subsets, do these two events have any elements in common? You can see that the even event and the event of less than 4 have the outcome 2 in common, so they're not mutually exclusive. So the answer to number 7 is no. On the other hand, the even event and the odd event don't have any events in common, so the answer for 8 would be yes. Okay, so hopefully that's given you a little bit of practice with that. Let's go on and look at some of the exercises that have to do with probability models. So consider the probability experiment of rolling a 4-sided dice. So this is the same sample space that we just dealt with in the previous exercises. And so a probability model is an assignment of fractions between 0 and 1 to all the simple events. So here is, now see, E1 is the event that when you roll the dice, a 1 appears. So this is the probability of E1, which we're going to assign as 2, 6. And then you can see here that the probability of E2 we're assigning as 1/6, and the probability of E3 is 2, 6. Of course, I'm writing this as so they're all over the same denominator. And the probability of E4 equals 1/6. So, I mean, you might have expected that the fractions would all be the same, and that's what you'd expect for a fair dice. But here, the question is this a valid assignment of probabilities? That's the question. This is on page 270, question 6. The question is, does it satisfy all of these 4 conditions? Well, obviously the fractions here are between 0 and 1. And we're assuming that these have been assigned, that the probability of the empty set is 0, the probability of the whole sample space size is 1. And then The question is, do these probability of all the do the probabilities of all the simple events add to 1? So we could just add these up and see whether they come to 1 or not. And you can see this 1, 2, 3, 4, 5, 6. So they satisfy number 3. So properties 1, 2, and 3 are satisfied. And you would check, like, for example, if I'd put that this was 2, 6, 1, 6, 2, 6, 2, 6, it might look okay, but they wouldn't add to 1, so it wouldn't be a valid model because they have to add to 1. But we don't know. The question is now, this is what I'm going to ask you guys. What is it? Does it satisfy this last one? The probability of the union of mutually exclusive subsets equals the sum of the probabilities of those subsets. Well, that might be a little bit hard because, but then still you can do a few tests and see, what do you think? Do you think 4 is satisfied? And I'm going to pause the recording, resume recording. Okay, so now let's just consider what this might mean. Well, it means that the probability of E12 that's either 1 or 2 would be the union. E12 is the union of these two simple events. Well, that means this probability would have to equal 2, 6 plus 1, 6, which equals 3, 6, which is 1/3, but right. 2, 6 plus 1, 6 is 3, 6. That's going to be 1/2. Well, let me write this out explicitly. 3, 6. That's the one problem with probability. Subject to probability is you end up with fractions. Well, that's 1, 2. And then we could have, how about the probability of E3, 4? Well, that should be, because the event would be the union of E3 and E4, then you're going to end up with the probability of being 2 and 1. So that's going to be 2, 6 plus 1, 6 equals 3, 6 equals 1/2. Well, that's interesting because then you can see that the probability that you could say, what about the union of E1, E3, 4? Well, that's the union of, there's no elements in common. These are mutually exclusive. So the probability of this event should equal 1/2 plus 1/2, which equals 1. Well, that's the same thing as the probability of the whole sample space. And you can see here, the union of this actually does equal the sample space size. So the only way to really get a contradiction with E4 would be if we gave more probabilities. Like if I defined the probability of E23 instead of as 3, 6, or 1/2, if I defined it to be something else, so that so it wasn't equal to the sum of these ones here. So to get a consistent probability experiment, the point of this problem is that you want to just assign probabilities to all the simple events, then use property 4 here to build up all the probabilities of the other ones by unioning up the events, because you can make any subset as a union of as a different union of simple events. So that's you can automatically satisfy number 4 as long as you have satisfied the first 3. Okay, so that may have been yes. And so then the question here, and this is a question maybe for this problem. Number 3 here is, let's consider that. What's the probability of E even? And I'll pause the recording here. Consider this. Well, E even is going to have the 2 and the 4 in it. So we're going to have, this is going to be the probability of E2 plus the probability of E4, which equals, so what is E2? E2 is 1/6 and E4 is 1/6. So this probability is 1/6 plus 1/6, which equals 2/6, which equals 1/3. Is that what you guys got? Let me, okay, so now we're recording again, and I just wanted to point out that you might think this was 1/2, right? That would be the natural thing if we were dealing with classical probability in which all the outcomes were equally likely. And that's what we will do in a little while. But for this model, we have 2/6, 1/6, 2/6, 1/6. So the evens and odds are not equally likely. This is twice as likely to end up with a one and with an odd outcome rather than even outcome. So what we have to do is use that rule that since the even um, event or subset is the union of these other two subsets, which is E2 and E4, the probabilities have to add. These are mutually exclusive, no elements and no outcomes in common. So it's going to be 1/6 plus 1/6 is 1/3. And so the probability then of E odd will similarly equal 2/6 plus 2/6 equals 4/6, which equals 2/3. Oh, by the way, let me show you how one of the nice things about WX maxima is, let's say that I didn't want to have to do these fractions. You can put in here 2/6 plus 2/6, and it doesn't give you four, it naturally gets you the lowest common thing, and it doesn't give you a number. It does it numerically as a fraction. So you can use if you're, you know, don't want to sort of rely on your native skill with fractions, you can use WX maxima as a fraction calculator where you get the number as 2/3. So I'd much rather you report, for example, 2/3 rather than 0.666. If you put this in a normal calculator, you get some number, and that's sort of more like it's less clear what's going on in that case. Okay, so there is, and then here's another sort of question in which you could ask the similar question, if whether this is valid and whatever. Okay, now we'll go on to the classical probability model here. And so remember, a model is an assignment of fractions to every event. Now, so let's say we have a sample space, and we have simple events. Like if we had a four-sided dice, or if we had say we had a six-sided dice, we would have like 1, 2, 3, 4, 5. We'd have these simple events. And so if the classical probability model wants to assign, say, all the simple events are equally likely. Okay, so if they're equally likely, then and that means that they're all the same. So we have the probability of E1 equals E2 equals E3 equals the probability of E4 equals the probability of E5 equals the probability of E6. Maybe I should have stayed with the four-sided dice. Now, but the requirement is that these things add up to 1, because if I add up, all of them have to add up to 1, which is basically saying, because the sample space is the union of all the simple events, it's basically an extension of that fourth probability property, that is. Okay, well, this has to add up to 1. Well, since they're all equal and there's 6 outcomes, what you end up with is here 6, say, times the probability of E1, which is the same as any of them, will equal 1. Therefore, the probability of E1, and so the probability of E2, E3, E4, E5, E6 is equal 1 over 6. Well, what was the 6? Well, this was the actual sample space size. So we can say that the probability of E1 equals 1 over the sample space size. And this is going to be true for any probability experiment. If you have the probability of a simple event is going to be 1 over the sample space size. Now, let's consider the probability of a general event. Well, E is going to, this is going to equal, if the general event, say, is E1 union E3 union E5, then this is going to equal the probability of E1 plus the probability of E3 plus the probability of E5, which is going to equal 1 over the sample space size plus 1 over the sample space size plus 1 over the sample space size, which equals 3 over the sample space size. Well, what is this 3? Well, it's the number of elementary outcomes needed to produce this set here. So this is really the number of outcomes in the event divided by the number of outcomes in sample space. And this is going to be true in general. So this is why the classical probability model is nice, is it just reduces to counting. The probability of an event E is always the number of outcomes in the event divided by the number of outcomes in the sample space. That's our this rule produces the classical probability model, and it produces all the events, all the normal situations that you think of. For example, that if I have just a coin toss, the probability of heads has to equal the probability of tails. They both have to equal 1/2. And so that's what's going on with that. And the same thing with a dice. Here's 1/6, so that the probability of a dice is 1/6. And so we can figure out in general, just by counting, what's going on with any of these situations. So let's do some do a few more experiments with compound examples. So this is in the context of classical probability. Consider the probability experiment of tossing a coin twice. So you toss it first, then you toss it again. Then we're going to ask, what's the size of the sample space? And then, well, this actually is an earlier problem. I want to do one that actually, this is just labeling the outcomes. Okay, well, let's do this. Let's do these. This is number 8 is preliminary to doing number 9, which is what we're going to get to review this. Okay, so this is on page 272. Number 8. So let's try to work on these two, and I'm going to